right, so now it's time to find the inverse of a function algebraically. And this one can sometimes get some students tricked up. So I wrote down the steps that you can follow. It's fairly basic, but obviously there's some algebra that takes place here that students have to remember, and that's where usually things get tripped up. So the idea is, guys, when we have a function in function notation, f of x equals, then we're just going to want to follow the steps. And step one is replace f of x with y, swap the x and the y's, and then solve for y. Oh, and I don't know why I didn't add this, but really step number 4, which I should add in there, is replace y with f inverse of x, because that's exactly what we're doing, is we're finding the inverse of that, right? So that's kind of the important ideas. Now, again, this swapping x and y all ties back into, example number 1, as far as looking at the graph and its function and looking how those points are swapped, as well as understanding the domain and the range and how those are swapped. And then, which actually I didn't mention, so let's actually look at that real quick. If you look at this pink, graph, here's going back to, our example 2. If we look at the domain of our function, right, the domain of this function is x is greater than 0. Well, look at the range of this function. The range of this function is y is greater than 0. So you can see how they're exactly the same. And the range here is from 2 to 0. And the domain now of the inverse function is from 2 to 0. So you can, again, just kind of reiterate how the domain and the ranges are swapped for your inverse functions. And we'll go and take a look at that. I'll go and pick some problems so we can kind of see for that. So the other thing I just wanted to mention is when you have a function that's written as an equation, like already y equals, then we can just skip number 1. Just go right into step number 2, swap the x and y's, and solve for y. So it's really kind of like as basic as that. Now, I also wanted to mention to you that I took all of these equations and I put them into Desmos. So therefore, what you can do here is you can actually go ahead and test your answers. And I'm actually going to do y equals x line. I'm actually going to put that in there. And then so once you find the inverse, if you just want to plug in what your inverse is down below, then what that will do is, put your inverse down below, and then you can kind of check, make sure the symmetry is exactly what you were thinking it to be. Let me see. Uh-oh, did I? No, okay, I closed that, but I guess I did that. All right, so let's go and take a look at, the first example. So the first example will kind of break down step by step. And then for the other ones, I'll kind of move a little bit quicker so you can kind of see more of the algebra and not so much like, oh, swap f of x with y. I don't think you need to see that step every single time. Or even swapping x and y's. I'll start skipping over that first as well. So in the first example, though, we have f of x equals 2x. So what we're going to do, step number 1, is we're going to replace f of x with y. And we're going to set this equal to 2x. Now, you don't really actually have to swap f of x with y. You can actually continue using f of x. There's not a problem with that. But as far as algebraic manipulation, it's much easier to be writing y than f of x. And where, again, at y and f of x are kind of interchangeable as far as output values of a function. So therefore, it's just easier to use y than f of x. But if you want to continue using f of x, there's no mathematical rule you have to continue using f of x. Just remember, though, the idea is when you solve for f of x, you're actually solving for the inverse function. So that's why kind of using the y is also still helpful. Okay, so that's step number 1. Now, step number 2 is we're going to swap the x and the y's. So I'll just say x equals 2y. Okay, and then step number 3 is just solve for y. So to solve for y in this case, I'm going to just divide by 2 on both sides. And I get x over 2 equals y. And then step number 4, I think that was step number 4, replace y with f inverse of x. Now, typically we like a function to be f of x equals, or f inverse of x equals. So I'm going to swap the x over 2 and the y. Just going to rewrite that as f inverse of x. I'm replacing that with y is equal to x over 2. And then also notice that you could also, that is the same thing as f inverse of x is equal to 1/2 x. Okay. Now, when identifying the domain and range, let's go back, and now what we're going to do is I asked you to determine the domain and range of our inverse function. And again, if we know what the domain is of our inverse function, we know that's the range of the function. And the range of our inverse function is the domain of our original function. So we're just going to practice find the domain and range of here. And again, the tricky one would be finding the range, but the range of the inverse function is just the domain of our original function. So we can, just get some more practice with that. So as far as the domain here, well, this is, this equation is a linear graph, 1/2 x. So my domain is going to be all real numbers. Let's use domain in a different color. Let's use red. So my domain in this case is going to be -infinity to infinity. And the range is the domain of my original function, which I can just look up here and say, all right, the domain of that is all real numbers. That's a linear equation as well. So therefore, the range here is going to be all real numbers. Okay. Now, I do just want to kind of show you what Desmos, like what that would look us. Oh, it's not looking that way. That kind of stinks. All right. That got messed all up. Guess I won't do that again. Okay, sorry about that. A little technical difficulty. Let's go back then to example 3, and I guess I'll pop it up. So we found the inverse function. We don't have inverse notation in f of x, so I'm just going to use it as another function, equals 1 divided by 2x. Oops. Okay, and you can see that these graphs, the two blue graphs, are reflected about that red graph, right? So therefore, we can kind of show and prove that my functions are inverse of each other. So for each one of these problems, if you just want to kind of write the function, the inverse that you found below it, and just check that symmetry, that's what I basically created all that for you to do. All right, but now let's kind of get into, the algebraic operations. I'm not going to go back and revert to Desmos because that's just going to take too long, but I wanted to provide that as a resource for you to kind of go back. All right, so from now on, whenever I have an f of x, I am just going to rewrite it as a y. So I'm already going to swap the variables. So let's just go ahead and rewrite this one. Let me double check. Man, this all got messed up. Okay. So we can go ahead and rewrite this. I'm not going to write the step 1, 2, 3, and 4. We can rewrite this as y equals 1/3 x minus 1. Swap the variables. X equals 1/3 y minus 1. Okay. Now to solve for y, I got to use inverse operations, but also not only using inverse operations, you got to make sure you use reverse order of operations. That means we're always going to undo addition and subtraction first. Ooh, multiplying by a fraction. Remember, multiplying by a fraction is the same thing as dividing, right? Multiplying by 1/3 is the same thing as dividing, or multiplying by 1/2 is the same thing as dividing by 2. So if I want to get rid of multiplying by 1/3, I could just multiply it by 3/1, or just 3. I like to do 3/1, though, just to make sure students understand that, they're going to multiply to 1. Now, the important thing is I am multiplying this whole side by 3/1. Here's a big mistake. So again, these multiply to 1. So I'm just going to draw lines through them. It's not like they're canceling out. They multiply to 1, and 1 times y is just y. But the really important step here is 3 times 1, or 3/1, is multiplying by the x and the 1. So you got to put parentheses in there, because if you just don't, then it's just 3 times x, which is incorrect. It's 3 times x plus 1. So you got to make sure now we apply distributive property here. So I get 3x plus 3 is now equal to y. And now I can revert this with my inverse in notation. So f inverse of x equals 3x plus 3. Okay. Now the domain of that, that's going to be a line. So as far as finding the domain, I'm just going to say -infinity to infinity. If I wanted to find the range of this function, I also know it's a line, so it's it's unrestricted as far as the range goes. But you could also look at the domain of the original function and say, oh yeah, it's unrestricted as far as the domain of the original function. So that means the range of the inverse is going to be from -infinity to infinity. Okay. All right, so in this example, this is one of my examples where I said, it's already in an equation. So guess what? We don't need to swap y with anything. We can just go ahead and swap the x's and the y's. We don't need to replace y. We already have y there. So if I write this as x equals 3 over y minus 1. All right, so now it kind of comes back to that fractions, right? When we had this 1/3 y, we wanted to get the 3 off the denominator. So when we multiplied it by 3 in the numerator, what happened was that multiplied equal 1. That exact same process is what we're going to want to do here. If I have y minus 1, my denominator, if I need to solve for y, I need to get y minus 1 off the denominator. So I'm going to multiply it by y minus 1 in the numerator. And just like I did over here, whatever I did on one side, I have to do on the other side. I'm going to do that exact same over here. So now I'm going to multiply by y minus 1 on the left side. Again, here, y minus 1 divided by y minus 1, because that's like a multiplication up top, that divides to 1. It doesn't cancel out, it just divides to 1, leaving me with a 3. So now I can apply, actually I don't need to apply distributive property. I could apply distributive property, but that'd be actually too much work on myself. Because again, remember, I'm just trying to solve for y here, right? So look at my operations. My y is being subtracted by 1 inside the parentheses, and then it's being multiplied by an x outside the parentheses. So following that reverse order of operations, I'm going to divide by x first, and then I'll have y minus 1 equals 3 over x. Then I'll just simply add a 1 on both sides. And now I have f inverse of x is equal to 3 over x plus 1. Okay, so the domain of the inverse function of this function, remember, is going to be the range of the original function. And if we look at this, if I wanted to talk about the domain, we know that, going back on this like implied domain scenario, it's true for all real numbers except for 0, right? Because 0 is the only value that makes the denominator equal to 0. So my domain in this case, which is, again, the range of the original function, is going to be from -infinity to 0, union 0 to infinity. Or, also could just be stated, all real numbers except for 0. Now, as far as the range goes, again, to find the range, the easiest idea would just to go back to the original function and say, what is the domain of the original function? Because the domain of the original function is the range of my inverse function. And if we look at this, I'm not going to do any math. I'm not going to write it out. What number makes the denominator equal to 0, right? Again, we have another rational function. So we want to find the values that make the denominator 0. And there's only one number here, which is 1. So my range is going to be the set of all y values except 1. So in interval notation, in set notation, we want to make sure we clarify x's or y's. But for set notation, we can just rewrite this as -infinity to 1 union 1 to infinity. All right, getting on to the next one. These ones get some students tricky. I do have some, we will do some more examples. I only decided to do one for my notes because I think once you do the process once, it's the same process over and over. But, from experience, a lot of students, get tricked up with these when you have two x's, one in the numerator, one in the denominator. So to speed this along, I'm going to replace f of x with y. And then I'm going to swap the variables. I'm just not going to show like multiple steps there. So therefore, by doing that, I obtain now x equals y plus 1 over 2y minus 1. All right. Now, like my previous example, I got to get my y off my denominator. So I'm going to multiply by the denominator on both sides. Okay. Those divide out, and now I am left with the equation 2y minus 1 times x equals y plus 1. Now again, we're trying to solve for y. And this goes back to an Algebra 1 problem. A lot of students forgot all of this stuff, but we need to solve now for y. And you can see we have y's on both sides. So the first thing we need to do is get rid of our parentheses. So that means I need to apply distributive property with the x. And then I need to group the y's to the same side so I can isolate them. So I'm going to multiply by x on both sides, or x through. So therefore I have a 2yx minus x equals y plus 1. Get the y's to the same side, right? So we can isolate them. So therefore, I am going to subtract a y on both sides, and I'm going to add an x on both sides. So I'm going to do this kind of the same one because I don't run out of space. So by doing that, those add to 0, those add to 0. So I'm left with a 2yx minus y is equal to 1 plus x. Okay. Now, previously what we did is previously doing some problems similar to this, we could combine like terms and then solve for y. But in this problem, we can't combine the y's because this has a 2 and an x with it, and this one, does not. So they're not like terms. So we need to solve for y, we can only have one y. So we got to figure out, well, how else can we do that? Well, we can factor out a y because a y is common on that side. So if I factor out a y, I'm now left with, by factoring out a y, which is kind of same thing as like dividing out the y, I'm left with a 2x minus 1 equals 1 plus x. And now, to solve for y, I just divide by 2x minus 1 on both sides, and something really, really interesting happens here. As you notice, I have the exact same function. Oh, I'm going to set this as f inverse. And what you see here is a function and its inverse are exactly the same. And that's really, really cool. If we kind of go back to this, what is the dx plus 1? If you look at this graph and the original y equals x, what we'll see is this graph is perfectly symmetrical about the y equals x line. So it actually has symmetry about the y equals x line. That's why the function and its inverse are exactly the same. So it's kind of an interesting example. The other ones that I'm going to do in this case will not, that's not always the case for those types of functions or for any really function. It just happened to be that was the example that I decided to do. But we will do some more, where they're not exactly the same. Now let's kind of get into identifying the domain and range here. So the domain of this function, I need to kind of, I guess I can do it over here. So the domain is going to be the set of all x values. Jeez, oh man. And again, I'm finding the domain and range of my inverse function, just a little FYI. So the domain of my function here, of my inverse function, is 2x minus 1. So that's going to be, what values make that 0? That's going to be 1/2. So if you set this denominator equal to 0 and solve, you get positive 1/2. So that's going to be 0 to 1/2 union 1/2 to 0. Oops, what am I doing 0? That's infinity. There we go. And then the range is, I'm going to want to go back to my function here. Oh, actually the range again is going to be the exact same thing. What you'll see is for the range is you want them to have the same if the range would be the domain of the inverse, which is the exact same thing. So that's going to be domain and the range. I'll just actually kind of like bring those together. That's the domain and the range. All right, so now let's kind of get into some cubic problems. So same kind of thing. We haven't talked so much about cubic expressions, but again, just kind of very similar to our quadratic, and we'll just kind of, follow really the same steps. Now for these, just to kind of again, speed things along, I'm going to swap f of x with y and then swap the variables. So now my next step is x equals the cube root of 2y. Oh, well, at least the one thing I guess I should note. I should know. We'll get to it when we get to it. All right, so now we need to solve for y. So you can see that y is under the cube root. So to undo the cube root, that means I need to cube both sides. Okay, by cubing both sides now, I get x cubed equals 2y. Now, just to solve for y, I can divide by 2. I don't like dealing with having a 2 in the denominator. I prefer to write my notation as f inverse of x is equal to 1/2 x cubed. That's the way I kind of prefer to write my notation. So let's go and take a look at the domain. And here's what I was talking about, some things to notice. So the domain of the cubic function, if you remember from our parent functions, the domain is unrestricted as well as the range is unrestricted. So if I'm looking for the domain of this function, I'm good. The domain here is just going to be all real numbers. There's no restrictions on taking the cube root or cubing a number. So my domain, I can just say from -infinity to infinity. Now, the range of this function, again, is the domain of the cube root. But again, here's the important thing. Remember, we are restricted when we take the square root of a negative number. Our square root of a number, it has to be positive. We're not restricted on taking the cube root of a negative number because, for instance, the cube root of negative 8 is negative 2. Why? Well, because negative 2 times negative 2 times negative 2 equals negative 8. So as long as it's an odd root, or as long as it's an odd index, we can take the root of a negative value and we'll have a negative answer. It just only doesn't, we're only restricted when we're taking even roots. And if you remember what this graph looked like, it looks like just, it's like the sideways kind of like little S-curve that we're dealing with. So the range, which is the domain of this cube root function, is also unrestricted. All right, now let's go and get into this function, which is in a vertex form of the cubic function. So I kind of like this one just because it makes us, again, follow these order of operations. Let's use green. So we swap our variables. X equals y minus 2 cubed plus 4. Okay, now again, we have a lot of things that are going on with the y. It's being subtracted by 2, it's being cubed, and it's being added by 4. So we got to use our inverse operations as well as reverse order of operations. Always undo addition and subtraction first. Then, usually you want to undo, we can't undo this addition and subtraction though, because it's inside of the parentheses, and these parentheses are cubed. So now I need to undo cubing, which would mean taking the cube root. So I take the cube root of both sides. And what I get is the cube root of x minus 4 is equal to y minus 2. Now I can undo subtracting 2 from y by adding a 2. And what I get is f inverse of x is equal to the cube root of x minus 4. And then close my radical, and then plus 2. Now again, the cool thing about the cube function is I know there's no restrictions on cubing or the cube root. So my domain and my range is just going to be the same. Let me try if I can. Oh, let me see. Haha, sweet. Sweet. So covered that. All right, now let's get into some stuff where it's in the radical, right? So now we're definitely going to have some restrictions because we know once we have variables in the denominator, we got the values that make the denominator equal to 0 are not in our domain. So now let's go ahead and swap them and kind of see what happens with this. All right, so therefore swap the x's and the y's. So that's 1 over y cubed plus 1. All right, now again, we have this variable that we're trying to solve for in the denominator. So therefore, like we did in the other examples, we got to multiply it on both sides to get rid of it. So y cubed plus 1. All right, so that now divides into 1. So we're just left with 1 on the left side. I don't need to distribute this like in that last example, this example up here. I don't need to distribute it because I don't have y's on both sides. In this case, I only have my 1y. It's being multiplied by that x, but if I just want to solve for that, all I need to do to isolate my y is just divide by x. So let's just divide by an x now. And then I don't need the parentheses anymore. Y cubed plus 1 equals 1 over x. Subtract 1, subtract 1. So oops. I'm not done yet. I was like getting so quick and fast. So then I have y cubed equals 1 over x minus 1. Kind of taking me a little bit longer on this one. So now we need to undo the cubing because we're not solving for y cubed. We're trying to solve for y. So I need to take the cube root of both sides. And by doing that, I get a final answer of f inverse of x, which is now my y, right? I replace that, is going to be the cube root of 1 over x minus 1. Okay, so this brings in some interesting things on my restriction, which I'm going to have to fit in here. So we know that the cube root is is unrestricted. So taking the cube root, there's no restrictions, positive, negative, or it doesn't matter. However, we do have a fraction where the variable is in the denominator under my cube root. So what that tells me is now my restriction of, rational functions here is going to come into play, meaning that x, the only value that x cannot be is 0. Not because you can't take the cube root of 0, but because 0 is now in a denominator. So my domain of my inverse function here is going to be all values except for 0. And then to find the range, I need to go back to my original function and determine, all right, what values make my denominator equal to 0? And, if we just wanted to solve this one, I know you could do this in your head. But again, just wanted to reiterate that negative value motion. If you take the cube root on both sides, the cube of root of -1 is equal to -1. So what that means is -1 makes my denominator of my original function 0. So -1 is not in the domain of my function, and therefore it's not in the range of my inverse function. Again, -1 cubed is -1, -1 plus 1 is 0. So my range in this case is going to be -infinity to -1 union -1 to infinity. All right, last but not least here is my h of x, or my last function. Now I have a cube root in my denominator. But again, if you've kind of followed, you'll be like, all right, this is kind of like the same thing over and over. And yeah, that's really my idea, is really to drill down this process into you. So by the time you've done these, 8 examples, I can give you any example you want, and you would feel comfortable doing them on your own. So we replace f of x with y, swap the variables, and we're left with x equals 1 over the cube root of y minus 1. We have a variable in the denominator that we're trying to solve for, so let's multiply it. So cube root of y minus 1 on both sides. Cube root of y minus 1. Those divide to 1, so therefore I'm left with the cube root of y minus 1 times x equals 1. Now again, in this case here, I can't really do anything else anyways. I need to solve for this y, so first thing I can do is divide by an x on both sides. I kind of like using black. So therefore, I now have the cube root of y minus 1 equals 1 over x. So kind of very similar to what I did over here. However, in this case, now I need to get rid of the cube root. So therefore, I'm going to cube both sides. And by cubing both sides now, I get y minus 1 is equal to 1 over x cubed, right? It's really 1 cubed over x cubed, but 1 cubed is just 1. And then I can just add 1 to both sides. We don't need to write that. Add 1 to both sides, and I can rewrite this as f inverse of x is equal to 1 over x cubed plus 1, right? I think you guys hopefully can follow the steps. If I want to find the domain of this function, we can see that, again, this is a rational function. So again, our implied domain of rational functions, you cannot divide by 0. So 0 is going to be the only value that, in this case, does not work. So -infinity to 0, union 0 to infinity. And then we go and look at the range, and the easiest way to look at the range here is, again, looking at my original function, looking at the domain of my original function. Now we have the cube root, but again, that is unrestricted. So the only thing we're worried about is making the denominator 0. So we say, all right, what values make my denominator 0? And then again, that case is only going to be for the number 1. So in this case, we'll just have -infinity to 1 union 1 to infinity. So there is a basic multiple examples for you guys to hopefully kind of follow the operations for inverse operations, because we do kind of cover some stuff that you haven't covered in a while. So I think it's a good review to kind of go over these different types of examples. And then again, the main important thing that I think is, to take away from this is that when you're trying to find the domain and the range of a function, just remember that, to find the domain is pretty straightforward, but to find the range, just find the domain of your inverse function, and then you're all set. So now what we're going to do is we're going to move on to our next examples, which is going to be looking at the restrictions of our function. So that will be in example 4 coming up next.